Hello, my name is Mike Dunne. I'm a co-founder of Inertia Enterprises, along with Jeff Lawson and Dr. Annie Croucher. I serve as the CTO. I'm responsible for the design and delivery of the fusion pilot plant and all of the technologies that fit within it. Now, together, we founded Inertia because of a monumental breakthrough in fusion science. Of the many dozens of approaches to fusion that have been explored over the decades, it turns out only one approach has been proven to get to that point of net fusion energy gain. And Inertia has the exclusive rights to take forward key intellectual property to take that technology to market. This is why we see ourselves as the commercial fusion company, no longer searching for elusive physics, but rather with a focus on harnessing technology, building a supply chain, and taking that to market. Now, this approach has attracted very substantial investment from our partners. Really happy to recognize Bessemer Venture Partners as the lead, with Google Ventures and many others you can see on the slide here that are taking us forward over these next few years in order to get to that point where we can build, turn on the fusion pilot plant. This has all been enabled by a breakthrough that was achieved on the National Ignition Facility at the Lawrence Livermore National Lab in California. But I can tell you, getting there was not easy. It took perhaps 5 generations of high-power laser systems. It took classified codes and data, even to establish the right regime in which fusion ignition could occur. And then, after the NIF turned on, it was over 10 years of experimental tuning to reach that point of ignition, to get to fusion burn, to get to energy gain. And I'm really proud that it was my co-founder, Annie Croucher, and the wider team at Lawrence Livermore National Lab that reached that point in December of 2022. And since then, those results have been repeated many times. The gain has increased again and again. And perhaps this time last year, got to the point of a gain of over 4, which is what's called Q scientific. This is measuring fusion energy output compared to laser energy delivered. The other thing that was learned over this past 10 years or so is that even small changes in the configuration of the laser or the target or how they're combined together, even small changes which the codes say should all be fine, can lead to devastating loss of gain, can lead to essentially quenching of the fusion burn in ways that are simply not understood. And so there is a very narrow window of operation that has been validated by the NIF, and we should be respectful, I think, of what we've learned over that period. There's been a real salutary lesson for all of us. Perhaps history showing us time and again, speaking as a plasma physicist, plasma physics is hard. It's an unpredictable and perhaps unforgiving science. And this is why the breakthrough by Annie and her team is such a game changer. And so Inertia's strategy is then quite simple. It's to stick as closely as possible to that proven window of science, and then take the most direct path, the lowest risk path from there, to integrated operation of a fusion pilot plant and to commercial fusion deployment. Version 1 of the plant, the pilot plant itself, perhaps will not be the most beautiful of pilot plants, certainly not the most optimized. It's there to teach us how an integrated plant can work. I've spent my career, most of it, designing, building, and operating large-scale, complex research facilities. Each time, as we turn them on, there are complexities, there are surprises in their integrated operation. And we've all seen this journey in our everyday lives, as how advanced technologies are deployed into the market. Everything from mobile phones that started off as bulky briefcase-sized devices, and are now these beautiful, sleek works of art that we carry around, and then maybe all the way over to rocket science. The first version of the Raptor rocket that sits in the SpaceX Starship. Version 1 was a complete mess of flanges and welds, actually by design, so the team could learn. Sometimes it would blow up, sometimes it wouldn't work appropriately, so they could reconfigure. And that taught how to progress through version 2 to version 3, which is now an additively manufactured, beautiful, sleek system, that works, and powers that Starship. Similarly, we need to respect the complexity of the fusion pilot plant and not pretend we can optimize it too early. We need to be able to learn and learn at full scale. We need to be able to design in margin and flexibility to enable that learning, to allow us to respond to the unknown unknowns and provide a pathway to continuous improvement, optimization, using data from that full-scale system. And so our approach at Inertia is to build in 4 technology pillars as we piece together this pilot plant. The first is at the heart of why Inertia exists at all. It's the performance of the fuel target itself, using that only known approach to fusion physics that produces energy gain and staying as closely as possible to that window of operation that the NIF has taught us. Now, fortunately, when we take a look at the integrated system level of our plant, we only need relatively moderate gain, somewhere between 15 and 20, in order to get to net power output to close the fuel cycle to get to that first plant. And then just a factor 2 more than that, a bit less, perhaps a gain of 35 or so, will get us to a gigawatt worth of electricity onto the grid. The second pillar is how we manufacture the fuel that provides that performance. We need to scale up from these lovingly crafted individual R&D prototypes, that take hours and days to make, to mass manufacture production lines that maintain acceptable tolerances, such as the roundness, the roughness, the placement of the fuel and so forth. If we can do that, then we can amortize the cost of these large-scale manufacturing processes across millions, actually hundreds of millions of targets per year, and so bring their unit cost down to around $1 or so a piece. The heart of the system is, of course, the high-power, high-energy laser. The NIF has taught us what the output of that laser needs to look like in terms of its pulse shape, where the energy goes, its bandwidth, and so forth. But the technology of the NIF was designed to be an R&D device, not a power plant. And so we need a change in technology for our system. And actually, it's a similar transition to what has happened in almost every other part of our lives across society, a transition from vacuum tubes to semiconductors. In our case, flash lamps that power the laser to semiconductor laser diodes. And we need to scale up that market of these currently boutique laser diodes, scale up the market by a factor of hundreds, maybe a factor of 1,000 or so. This will bring the cost down to an affordable level. And these laser diodes provide inherently the efficiency we need for a power plant, going from a wall plug efficiency of about 1% or so on the NIF to 10 to 20% using these semiconductors. They also provide inherently very high repetition rate, going from 1 pulse every hour or so to many, many pulses per second because of their inherent efficiency. And very importantly, they also provide us with a compact form factor that allows us to build these lasers in a factory, wherever it may be, and then truck ship the lasers to the plant. This modular approach provides us with a lot of flexibility, a lot of adaptability. It also is the approach to get to high availability of the plant, high maintainability, which you need for the type of base load electricity supply that fusion will be pointed towards. Now, of course, we know there will be surprises. There will be non-idealities in the fuel manufacture. Our codes say that a factor 2 or 3 increase in the laser energy from the NIF should be sufficient. But I guess our approach at Inertia is if you're going to build a big laser, you might as well build a really big laser. And so we adapt another factor of 2 margin on top, a factor of 5 overall to get 10 megajoules for our laser system so that we have real robustness, real margin for these unknown unknowns. And then finally, put this together in the integrated plant itself. And here again, our approach is to be as modular as possible so we can learn as we go in the areas that require the integrated plant to teach us, whether it be breeding and recovering the tritium fuel and maintaining its inventory at an acceptable level, or whether it be the heart of the system, the chamber that holds the fusion system. We don't have a material that can last forever. And so we adapt and develop a system that can be replaced periodically, a line replaceable unit all the way down to the chamber of the fusion pilot plant, and then protect that chamber wall with gas to let us use a simple conventional steel that provides us with a very direct path to market. Now, all of this, of course, is enabled by a very substantial suite of public and private partnerships. Inertia is funding perhaps the largest ever privately funded public-private partnership across the DOE complex, based at the Lawrence Livermore National Lab. And we also have partnerships across the vendor base, whether that be with the semiconductor companies, optics, lasers, large-scale energy manufacturing companies, and so forth. Perhaps the most important aspect of these partnerships is to build the vendor base, build the supply chain, everything from the laser glass to the optics to those fuel targets, of course, the semiconductors that lie at the heart of the laser, all the way through to the steelwork that makes up the plant itself. And what we've seen, even in these first few months of Inertia's operation, is the growth and engagement of that vendor base. You can see in this chart on the right, the map, the vendors that we've been partnering with just in the first 3 months of operation, forming and driving how we can scale up not only to that first pilot plant, but scale up to the rollout of the fleet afterwards, because our eye is always on that commercial deployment. The pilot plant itself, perhaps its most important aspect as we sit here today is to ensure that it is deliverable. That means we have a supply chain we can go to, materials that we can procure today, and materials and systems that are affordable. We need to be able to earn the right to operate at full scale, adapt and learn as we go, and optimize from there onwards. Because of the uncertainties in any large-scale system, we build in margin in every single aspect of this, and we build in adaptability through modularity to those operational uncertainties that will tell us how to build availability, it will tell us how to build maintainability, and it will tell us how to optimize for full commercial deployment. We do not need those things on day one, just like in any other part of our technology lives. We need to be able to learn and adapt, optimize as we go. Our starting point is some work that I led over a decade ago at Livermore Lab, putting together an integrated power plant design with many, many different partners. That provided a basis for how we close the fuel cycle, getting a tritium breeding ratio much greater than 1. Of course, closing the power cycle, this is a power plant, but also do so in a way that teaches us those concepts of operations and maintenance for rollout of the commercial fleet and for the supply chain that needs to put the pieces together for that fleet. And then importantly also teaches us all, including the public at large, what a fusion pilot plant really looks and feels like, so we're comfortable having it sitting next door to us, powering our cities and our wider society. So let me wrap up and summarize, perhaps the most important point, the reason Inertia exists is because of this breakthrough, this 60-year event that took us from exploring physics to knowing the physics regime that works. To then harness that and harness it with margin and adaptability. So because we want to be able to optimize as we go. Our focus as a company is on that fuel target design and of course the manufacturing at high scale, the targets that are needed for those fuel delivery systems. The laser itself, everything from the semiconductor diodes through to the integrated system and the supply chain that underpins all of that. And every step along the way to do so in the context of a self-consistent integrated fusion pilot plant design. So this thing can operate at scale and we can learn how to optimize it from there onwards. Our approach is to take that most direct path from the proven physics at the NIF to that commercial pathway for the pilot plant and optimize by learning at full scale. So finally, let me thank the organizers of the Fusion Report for this opportunity to present Inertia to you all. I'm looking forward to the panel discussion. I hope that of the many approaches being explored, others can find a physics basis and a pathway to a commercial deployment. Really looking forward to the discussion. The world for sure needs fusion. Thank you.